In this video, we will discuss how to calculate the band gap energy from UV-Vis data. This calculation is based on finding the derivative so that it gives us a clear idea of how we can find the band gap accurately and easily. So this is the origin file. Let me open this file. It is to be noted that I am using Origin 2018. I will provide a link to this file. This file has built-in calculations. So the only thing is that you will have to paste your data here, wavelength versus absorbance. And then it will calculate all the parameters here. Sometimes we require the data to be smooth because the data at longer wavelengths may have noise. And since we are discussing the derivative method, we need smooth data for that. Then in the next column, we calculate the absorption coefficient in per centimeter. This is alpha. I would advise that if you are not familiar with many of these parameters, then I have already made a tutorial video on band gap calculation from UV-Vis data in Origin. You can check the tutorial first so that you understand the terminology used here. So here, this is the absorption coefficient per centimeter. And you know how we got this 2.302. I have explained it in that video. We are taking the thickness of the material as 1 centimeter. Now keep this conceptual point in mind. The thickness is not affecting the band gap because it is related to the y-axis, and if it increases or decreases, it doesn't affect the band gap because the band gap is the intercept on the x-axis. So this will only change the y-axis values. Then the template converts the wavelength using 1240 divided by lambda. So it converts it into electron volts here. And this has also been explained in the previous tutorial why we use 1240 divided by lambda. And then here I am just reproducing the D column. This is alpha and this is for the derivative purpose. Then this column is showing the first derivative and it will be plotted automatically. This will be plotted automatically because we have auto selection here and it will plot the data as well. And then we have this column for the automatic calculation of the indirect value alpha h nu power 1/2. And here this column is calculating for the direct band gap. So the only thing here is that we have to put the wavelength versus absorbance values. So let me delete these values so the template becomes empty. And now I will put some values here. So let's go to the folder where I have the data set. Here, this is the ZNO UV-Vis experimental data, and this is the one with which I will explain the process. This is almost experimental data. So let's first start with this one. It is a known material. ZNO is a direct band gap material with a band gap of around 3.3 electron volt. So this band gap typically varies from 3.2 to 3.3 electron volt. So we have this data from 1100 to 300. Let me select this data, copy it, and then come here and paste it. So as we paste the data, it automatically calculates the other parameters and also plots the derivative. So here it has calculated all the parameters. Now first, since it has plotted the derivative for us, we will look at the absorption edge. To see this clearly, let me convert this to a scatter plot. Now let me zoom into this region. And here it is. We have the maximum. Let me use the data reader, and this is the value where we observe the maximum of the first edge. And this corresponds to the band gap of the material, and we can see that it is around 3.3 electron volt. So our first estimate is 3.3 electron volt. Now we move to the next step. We got a confirmation that the value is around 3.3 electron volt. So now come to the values here. We have the energy here and the band gap related values. So let's start with this. First I will check the indirect plot. So I select it and plot it. And we can see that this is the indirect plot. Now let's check the direct one. So select the direct and plot it. And here we can observe that we have a very sharp edge, so we go for the direct band gap here. Now the first thing we need to do is to make this plot more visible. And then very importantly, set the y-axis minimum to 0. Otherwise the intercept will not be correct. So now we have the plot. Next we draw a straight line along this region. Let me draw it from here to here. Let me increase the thickness and change the color to red. And now we can see that the band gap, this is 3 and this is 3.5. So this is around 3.25 and it is slightly less than 3.25. Let me use the data reader. As you know, the data reader works when we are on the data. So slightly adjust it and here it matches. So the value at which it intersects the x-axis is around 3.19. So it is approximately 3.2. So we can say that the band gap is around 3.2 electron volt. So plus minus 0.1 is acceptable. And here the derivative is giving around 3.3 electron volt. So both are consistent within acceptable range. So this is the way to calculate the band gap using the derivative method. Now why I am focusing on the derivative method? Because you will see in a moment when we go to another ZNO dataset where the y-axis values are quite high. This method becomes very important. So let's go to the other dataset. Let me close this one. Now again, go to the data. I delete these columns so everything is cleared. Now I go to another ZNO dataset. Here the absorbance values are much higher. Let me copy this data and paste it here. Then copy the absorbance and paste it as well. As we paste the data, again the derivative is plotted automatically. Now let me zoom into the edge region. Convert this to scatter plot so that values are clear. And here the absorption edge is around 3.28, which is approximately 3.3 electron volt. So again we note this value. Now let's check the direct band gap plot. Select and plot it. Now you can see that compared to the previous case, this plot is much higher. Sometimes it can be even higher than this. Now if I directly draw a line here, the band gap comes out to be around 4 or even higher, but the derivative is still showing around 3.3. So where is the problem? The problem is the y-axis scaling. Let me show this. If we rescale the y-axis step by step, the edge becomes clearer. As we reduce the scale further, we can clearly observe the correct edge. Now if we draw the line again, it comes around 3.2 to 3.3. So the correct band gap is still around 3.3 electron volt. So sometimes the data can be misleading. The derivative suggests one value while the raw plot may suggest something else due to scaling. So this is why we first confirm using the derivative method, because the derivative clearly shows the absorption edge. Thank you for watching this tutorial.